It was a blessed second when the Andromeda cloud, for the time being, turned into the Andromeda system. For quite a long time, how we might interpret the Andromeda world was restricted to ground-based perceptions. However, with advancements in innovation and the introduction of the James Webb Space Telescope, our comprehension has developed incomprehensibly. Now, things are going to change, as the James Webb Space Telescope has distinguished disturbing signs coming from the Andromeda system. These signals have sent shockwaves through established researchers, leaving space experts both motivated and inquisitive. However, what precisely do these signals mean? Above all, why are they creating such a ruckus among stargazers? Join us as, only 2 minutes prior, the James Webb Telescope shut down in the wake of receiving these disturbing signals from the Andromeda galaxy. Before we could see far beyond our eyes into the universe, cosmologists trusted the Milky Way to be the entirety of the universe. This lack of knowledge was fundamentally due to limited technological innovation for observing different galaxies and celestial bodies. Everything changed when we discovered the Andromeda system, which served as our first clue to knowing that the universe extends far beyond the Milky Way. In human imagination, everything began in the 17th century when Galileo Galilei's pioneering work with telescopes revealed the Milky Way's true nature. He saw that the Milky Way had various stars, challenging the prevailing idea of its solitary significance. Everything changed in the 1920s when Edwin Hubble discovered distant objects beyond the Milky Way using the Hooker telescope. Edwin noted that these celestial objects moving through the universe were galaxies, different from the Milky Way. One of these galaxies was the Andromeda Galaxy, or M31. While this was the first time we were aware of the Andromeda system, a Persian cosmologist, Abd al-Rahman al-Sufi, originally noted it around the 10th century. Due to technological advancements in the 20th century, space experts could see and comprehend the true nature and substance of Andromeda, which is an unresolved cloud comprising a tremendous system of stars, much like our Milky Way. Our galactic neighbor is about 2.5 million light-years from the Milky Way. Since its discovery, the way we study Andromeda has significantly advanced. We have moved from ground-based observations through telescopes to space observatories like the Hubble and the James Webb Space Telescope. Every step in technology has taken us higher than ever, assisting us in understanding the secrets of the Andromeda Galaxy. We now have more information and understanding of its composition and structure, making Andromeda a benchmark for studying the formation and evolution of galaxies. This has revealed more insights into the broader workings of the universe. Researchers believe that to have a better understanding of our universe and the Milky Way, we must study the connection between Andromeda and the Milky Way, especially given that the two galaxies are destined to collide in roughly 4 billion years. While studies and investigations have advanced, the James Webb Telescope recently received an unsettling signal from Andromeda. This disturbing signal perplexes researchers worldwide, prompting questions about its exact origin and potential implications. The James Webb Telescope's advanced sensors have detected surprising activity just within Andromeda's core. The signal sent back to researchers shows results that differ significantly from past observations, intriguing scientists globally. The signal indicates major processes happening inside the system, possibly connected to its incredibly massive black hole or previously unseen events. Notably, one of the latest discoveries suggests that Andromeda's mass might be much greater than that of the Milky Way, reshaping our understanding of the two galaxies. The James Webb Telescope has also provided detailed images and spectra of Andromeda, revealing the formation of new stars and their chemical compositions. This new information is significant for understanding cosmic evolution and potential scenarios for life. Moreover, the data from the telescope suggests increased activity in Andromeda's dynamic cosmic core, ultimately influencing its surrounding environment and future structural formation. By investigating the gravitational effects on stars within Andromeda, scientists gain insights into the distribution of mysterious dark matter throughout the galaxy, hopefully facilitating our understanding of its impact on the dynamics at play in the universe. Grasping dark matter and its effects on the universe is one of cosmology's greatest puzzles. Recent advancements by the James Webb Telescope have inspired various investigations worldwide as researchers delve into the mysteries of Andromeda. With more data coming to light, we are now learning more about the galaxy's past and future. So, what have we learned about the Andromeda system through various investigations? Andromeda has shown notable characteristics that distinguish it from other galaxies across the universe. Its sheer size commands attention, with recent estimates suggesting a diameter of around 220,000 light-years. This figure makes it one of the largest galaxies in the local group, significantly greater than the Milky Way. This tremendous scale contributes to its mass, comprising an estimated trillion stars, surpassing our galaxy in stellar count. Scientists also find the GST structure interesting. Unlike a regular spiral galaxy, Andromeda has a bulging center and a thick core encased within rings of dust and gas. This is undoubtedly a fertile ground for ongoing star formation, reflecting a dynamic universe shaped by continuous processes. Among its many features, one of specific interest is its core, characterized by a double-peaked emission indicating the presence of a very massive black hole, unlike but similar to that of the Milky Way. This offers significant insights into the nature and activities of these massive, matter-eating black holes. Andromeda is also surrounded by a halo of cosmic debris, comprising stars, planetary, and globular clusters, spanning many light-years in diameter. This cosmic shell tells a fascinating story of the galaxy's unique origins and history. The 460 globular clusters found in Andromeda also provide insights into the formation of stars in the early stages, offering a clear explanation of the development of star clusters and the early evolution of the galaxy. By unraveling the mysteries of Andromeda, space experts are one step closer to understanding the grand significance of dark matter. However, one question lingers: how do they account for its puzzling nature and the role it plays in the dynamics of galaxies? Andromeda boasts another distinctive feature: its satellite galaxies. Its halo structure consists of over 20 smaller galaxies, some of which are undergoing tidal stripping of their stars and gas. This process involves a larger galaxy pulling in and disrupting neighboring smaller galaxies, showcasing the dynamic nature of the cosmos. Development and depicting how systems develop and cooperate with one another over time raises intriguing questions about what the future holds for the Andromeda system, its shape, and the course of its development. This topic intrigues not just space experts but also those chasing to grasp the universe, especially with the possibility of its transformation from a spiral galaxy to a ring world. Andromeda's development evidence points to a process that could lead to other interesting blends, perhaps from cosmic impacts or close interactions with other systems. Assuming Andromeda is indeed moving in this direction, it implies that it has experienced numerous interactions with other galaxies since its inception. Ultimately, Andromeda's future relies on the inevitable impact with the Milky Way. According to these models, the impact is estimated to occur around 4 billion years from now. The consequence of such a collision is the formation of a new galaxy from these two giant celestial entities. However catastrophic the crash may seem, it is a natural part of cosmic development. Due to the vast distances between the galaxies, this cosmic crash will not be an immediate collision. After the impact, both galaxies would be drastically reshaped, forming new structures. The amalgamation of their gases and dust will spark new rounds of star formation, leading to a spectacular display overhead as the merging objects shine brightly. Such a cosmic event will result in the creation of a single elliptical galaxy. This type of collision is not unique, the universe has a long history of such occurrences. However, our direct involvement makes this event particularly significant to us. Additionally, the anticipated collision of the supermassive black holes at the core of the two galaxies adds more mystery to this cosmic spectacle, suggesting a complex and profound nature of cosmic evolution. The merger is expected to produce flares from matter being consumed by the black holes, resulting in extensive radiation. This process provides valuable insights into how galaxies evolve over their lifetimes and how black holes influence this development. However, it raises a crucial question: what will happen to our solar system after this merger occurs? Far from an outright destruction of the solar system, the dynamics and conditions of the nearby planetary system could be significantly altered. This implies possible orbital shifts or even ejections from the newly formed galaxy. To understand this mechanism, researchers can study the frequency of similar events occurring in the universe and contextualize the eventual fate of our own galaxy. It's essential to recognize that a collision between stars is a rare event in space due to the vast intergalactic distances. However, the gravitational upheaval could disturb stars' stable orbits, causing some stars, including our Sun, to change their trajectories. Such a change would undoubtedly disrupt conditions on Earth. One of the most critical changes humans could experience is moving further away from or closer to the Sun. This could lead to either warming or cooling effects. A warmer climate might cause ice caps to melt and sea levels to rise, while a cooler one could trigger another ice age. Additionally, the gravitational dynamics of such a merger could alter radiation levels reaching Earth, creating even more challenging conditions. In essence, the merger of the Andromeda and Milky Way systems illustrates the intricate relationships between celestial bodies. As the black holes in both galaxies draw closer over time, their gravitational influences could enhance the flow of high-energy particles reaching Earth, potentially increasing cosmic radiation exposure. The potential surge in radiation levels could pose a threat to ecosystems on our planet, as it might elevate mutation rates in populations and impact biodiversity. The rearrangement of Earth's natural orbit or its axial tilt following the black hole merger is expected to disrupt habitat distribution. The survival of species in ecological zones that may become inhospitable is one of the impacts of environmental changes experienced globally through shifts in biodiversity and ecosystem structures. While a few species may thrive under the new conditions, many would face extinction, and others would be severely threatened. The merger will likely lead to the formation of new stars, as clouds of gas coalesce and compress. If this process occurs near our solar system, radiation from these newborn stars could further modify the atmosphere, resulting in a radical change in climate and the entire biosphere. While it is true that these events characterize the grand narrative of cosmic evolution, it is crucial to place them in context and understand the timeline. The resulting events from the collision are far in the future, billions of years ahead, when humanity may have transformed significantly. We might be living in entirely different regions of the universe or beyond it. The insights gained from studying the Andromeda galaxy seem to be the key to understanding the evolution of our own galaxy and its future. The observable differences between Andromeda and our galaxy can be utilized to develop more accurate models for cosmic dynamics and evolution. The reassessment of Andromeda's size and mass is a strong foundation for this endeavor. Try since it straightforwardly illuminates our comprehension of the smooth way and its structure. Thus, it has broken our underlying presumptions about Andromeda. What's more, there is a need to rethink its importance in our cosmic neighborhood. Late information suggests that both the smooth way and Andromeda universes are equivalent in size, rather than our own being a lot greater. This goes against our understanding of the smooth way's role within the local group of galaxies and the gravitational force such a universe applies. While the smooth way today appears as a barred spiral galaxy, its structure could change due to its interaction with the Andromeda system and the collaboration that will undoubtedly occur in the not-so-distant future. As such, observing Andromeda's development helps in profiling the mechanisms behind significant cosmic changes. By looking at Andromeda's present status and assessing the direction of the ensuing collision with the smooth way, much can be inferred. Cosmologists would demonstrate the possible changes in star development rates and the distribution of gas and dust, in addition to the changes in both galaxies. This modeling is possible because of the technological advancements in astronomy that have significantly changed our understanding of space. Each campaign has become more extensive than the previous one. The venture began with the creation of the telescope in the mid-17th century, which led astronomers to observe the moons around Jupiter and the phases of Venus. Gradually, telescopes became more refined. The late 19th and early 20th centuries saw the design of larger and more powerful telescopes, making the world beyond Earth more accessible. While astronomers uncovered new celestial bodies like Neptune, ground-based telescopes faced challenges such as weather and light pollution. However, they managed to provide exceptional insights into the mysteries of the universe. With the introduction of the Hubble Space Telescope in 1990, we made a significant leap in space exploration. Hubble allowed us to view the universe from above Earth's atmosphere, effectively eliminating Earth's atmospheric disturbances. This resulted in greater clarity, depth, and observations than ever before. Hubble contributed to a better understanding of black holes, the universe's age, and the current expansion of space. The Hubble Space Telescope was joined by the Chandra X-ray Observatory, the Spitzer Space Telescope, and other space telescopes, which further expanded our knowledge of the universe. They observed the universe from space, bypassing the limitations experienced on Earth. Apart from light telescopes, radio, infrared, and X-ray observatories have also greatly expanded the cosmologists' options for sky observation. With these instruments, astronomers are not only able to identify but also study various phenomena. This includes the universe's microwave background radiation, star formation regions, and the remnants of cosmic explosion events. However, dark matter remains one of the most mysterious yet captivating elements that researchers are trying to understand. It constitutes approximately 90% of a galaxy's mass while being imperceptible. The nature of dark matter is such that it cannot be detected using standard observational means. Unlike other cosmic objects that are visible, dark matter is identified only through its gravitational effects on visible objects, radiation, and the large-scale structure of the universe. In the case of Andromeda, observational data indicates that dark matter originates from the galaxy's rotational dynamics. Stars in its outskirts exhibit rotational velocities similar to those at the center, which contradicts earlier predictions. This suggests that subtle components attributed to dark matter are surrounding and affecting the galaxy. Additionally, there is a massive amount of dark matter in Andromeda that extends far beyond the visible stars. Through its gravitational field, Andromeda's halo significantly influences the motions of satellite galaxies and star clusters that orbit around it. By examining orbital movements, astronomers have been able to determine how much dark matter is distributed in a galaxy. Such studies reveal that Andromeda's dark matter halo is not only massive but also extends, encompassing a 1,000,000 light-year radius from its center. Furthermore, the distribution of dark matter in Andromeda is unusual, with mass concentrated near the cosmic center while becoming more scattered outward. This distribution influences the formation and evolution of stars within the gas clouds throughout the galaxy, creating more spiral arms and altering the rates and locations of new star formation. Moreover, dark matter is speculated to have played a crucial role during the merging and collisions of galaxies, shaping the final forms of these vast events. Thus, uncovering the secrets of dark matter is a fundamental quest in modern astronomy, expected to pave the way for significant insights regarding the essence and evolution of the universe. The impending interaction between Andromeda and the Smooth Way is not merely a grand cosmic merger but also a collaboration of their vast dark matter halos. These subtle halos surrounding both galaxies will influence the dynamics of the collision and be essential in determining how the post-merger galaxy will appear. Observations of Andromeda have helped researchers fill gaps in understanding the formation and evolution of galaxies during the early universe. Through careful deep analysis of their structure, cosmologists reveal the small-scale processes that give rise to galaxies and transform them over billions of years. These cycles include the formation of spiral arms and the development of a central bulge, which typically occur after pairs of galaxies skim and merge. This grasping helps cosmologists refine cosmic models that are appropriate for the universe. Signals from Andromeda also contribute to improving the accuracy of the cosmic distance ladder through the comparison of the relative spatial distributions of nearby stars and the wider universe. The precision of methods assessing the size of the universe can be further enhanced. This adjustment is crucial as it clarifies fundamental cosmological parameters, like the Hubble constant, which is used to read the expansion rate of the universe. Additionally, by studying the stars that comprise the Andromeda galaxy and examining their chemical compositions, one can learn about the cycles of star birth and death, as well as the chemical evolution of the universe. These discoveries allow us to truly understand how nucleosynthesis and similar chemical enrichment processes occurred in the early universe.